Erik!
Hey, Charles!
How you doing, man?
I'm very good,
Now
thank
that
you.
is a really cool one.
Yeah?
That's the black hole?
It's the black hole. I think this is like energy efficient, whatever, you know. This is...
Perfect. So hey, we're in Dryad zone again.
We're in Dryad zone again. So yesterday we talked with Roger
Yep.
Barja about kind of, you know, the release of Dryad and Dryad Link to the academic community. And today we're going to kind of, you know, dive deep into the kind of, you know, the guts of the system, and in particular with Dryad. So why don't you introduce yourself to the channel now?
Hi, I'm Michael Isard. I'm a researcher at Silicon Valley in Mountain View. And I've been working on the Dryad for about 4 years now.
Nice.
Good. So yeah, so one of the things, you know, that Dryad Link obviously gives you is kind of, you know, the ability to run link queries in parallel on the Dryad infrastructure. So to kind of, you know, to get going, I would like to kind of, you know, write down a little query, and then, you know, let's kind of see how that kind of compiles down to Dryad, and then, you know, we can go and go deeper and deeper into the machine. So let's kind of do a typical query. RQ. This is typical MapReduce style query from W in words. Group W by this, and I got a little bit different dot length into G. Select length equal G dot key. Something like this, and then, you know, where do we do, let's do here in order by G dot key. So now they're ordered by length.
So you got a good shot of the back of your head.
Okay, good.
I want to
yeah,
move
so
this
you
over
see
a little
the kind of,
bit.
you know, the lack of hair.
So there is a query.
Okay, and let's assume that there are lots of different lengths here. It's not that it's lengths like between 4 and 12. These are not English words. These are strings between
like, you know,
1 and 10 million or something.
Exactly.
Otherwise, this order by is not going to be very interesting. Okay. So, let's see. So I'm not going to talk about how Link or Dryad Link works. I'm just going to say, as if by magic, there's an optimizer that's going to construct a distributed plan. So we'll talk about what that distributed plan will be, and then talk about how Dryad will execute that.
Perfect.
So
maybe we should move to that side of the whiteboard.
Okay.
Then, you know, we can keep the query there.
Okay.
For a kind of frame of reference.
So we'll start off with words. This is the table that we're reading stuff from at the start.
Okay.
And we're going to assume that you have some cluster and that you have distributed this data set across the machines in the cluster somehow.
Okay.
So in particular, it's split up into partitions. So you should think of this as, so I'm just going to draw, say, 5 partitions on here, and, you know, this could be 10,000 partitions, whatever, but this is some previous program or whatever has split this up, and these 5 partitions are each stored on a different computer.
Okay.
But
So
together, if you concatenate them, you get one big data set that is this variable words in the program.
Okay. So to talk a little bit about that, so this initial partition, is there any way kind of, you know, for the programmers to influence that, or is that just the kind of how the data enters the system?
So, yes, I mean, it depends how it was produced. So this might be just data that you loaded yourself, and if it was partitioned in a particular way when you loaded it, then you can tell Dryad Link metadata about that table. You can say if it was partitioned by hash of the word or something like that. You might have just loaded it using some standard bulk data loader, in which case it'll be probably partitioned just sequentially according to... Or it might have been produced by the output of a previous job, in which case it'll be partitioned, and that'll be stored in metadata as to, you know, whatever the convenient way for the previous job to generate it was. And I guess we'll see at the end of this what the partitioning is, and that will be about what it would be. Okay, so what are we going to do? We're going to group by length. So let's see, so these black things now are going to be files, and I'll make red circles be processes that execute. So what it's going to do logically is to fire up a process for each of these and just read the partition into the local process. And this is going to stream over all of the words in this partition, and it's going to get the length out, and then it wants to do a group by. So this is going to be done in the standard way that you would see in a MapReduce plan as well. What Dryad link the optimizer would probably choose to do is to do a hash partition by this key. So it will look at this data size and choose some number of partitions dynamically. We can talk a little bit about that later.
Yes, that was the question that we had yesterday as well.
But let's assume that it's going to choose 4 partitions because it decides that that's, based on the machines you have in your cluster, that's a good number.
Okay.
Then it will.
You feel free to kind of modify the query to make it more
so
clear how the plan works.
The fact that just to make a more interesting plan, I am going to modify it, I think, because the fact that you're doing group by and then order by means that really you should be doing this group by range.
Okay.
But let's move the order by to the end.
Okay, that's perfect.
We'll do some transformation in the select, and then we'll order by the transformed thing,
Okay.
so that there's really no ordering. That
Okay,
you would
let's
know
order
about
by
here.
we can order by the kind of size of the group, right? So then I want to have
Sure. Yeah. Okay. So
that gives me kind of for all the kind of I can see which words which length of the words is the maximum, right?
Yes.
So just write order by or words dot length or something.
Well, words equals G, so.
Well, no, but it's in the result, so it's okay. We don't have to we don't have IntelliSense on
That's
the
the
board.
problem with code, man.
Exactly.
Okay.
There's no IntelliSense. We want to kind of in the end order by
the largest word. Done.
Yes.
But anyway, fine. So this is going to be hash partitioned. So each of these is going to have some hash range.
Yep.
So what each of these guys is going to do is write out 4 outputs locally, one for each of the hash ranges, and then those are going to wire up so that these guys can then read them in. Oops. In the obvious way.
All right.
So we get this little cross product. So each of these writes out the partial hash partition, and then this reads all the bits that it needs from its 6 inputs. So now, and it's probably going to do a local sort in here, so these come out sorted, or it might do that here. But anyway, you can then within each hash bucket you can sort by hash code so that you get them ordered by you get them grouped. There's different algorithms you can use for this grouping, but
okay.
Somehow within each of these you're going to end up with the each group sequential because you've selected the bits from these partitions as they came in, and then also within this you're going to pipeline this select, so you're going to do this transformation.
Yep.
And then you want to do an order by some other quantity.
Yep.
So yep.
Yep. So I want to exactly.
So now, what we really want to do...
but I was just saying, I would like to kind of order by the size of each kind of, bucket there, right?
And something that we don't know the distribution of in advance.
Yes.
So in particular, there might be some sizes that are very common and some that are much less common.
Yep.
And so we don't just want to... And we don't even know what the maximum is.
Yep.
So we want to do this order by distributed, so we would like to distribute it. Let's assume again that it's going to pick 4 partitions. We'd like to do it such that each of these partitions has approximately the same number of elements to do its local sort.
Okay.
So what we really want to do is do a range partition based on the actual empirical distribution of this distributed data set. So the plan we're actually going to build is we're going to put a little sampling node here. So we're going to sample some small proportion of each of these. We're going to send them all to the middle. The middle guy is going to estimate an equal range distribution, and then it will send that range distribution out to each of these guys. So this reads all the data from here and also the range information so that then it can once again do one of these redistributions, so it sends the correct bits out to those ranges. So this is doing a little dynamic range partition, and then now this guy gets the inputs for just its range. It can do a local sort, and it can output that to a local partition, such that now if you concatenate all these together, you get the thing globally sorted. And as we discussed, now you name this table when you write it out to the file system. Now that also comes with some metadata that it has type information, and the metadata also includes the fact that it's ordered by and the expression that was used in the order, so that a subsequent plan, if you then started some new program and you used order by that as the first statement, it would know that it's a no-op, and it could just optimize that away.
Okay, so this is great. So I like this picture. So now the next question is, you kind of you mentioned a couple of times that you send values kind of from here to here. Mm-hmm. How is that done? Is that kind of is this guy pushing the values here, or is this guy pulling the values from the source?
Okay, so this is really a logical plan.
Yes.
This is a little DAG. So this is all directed arrows, and the vertices are processes that execute, and the arrows are data that gets transferred, and it's directed, and the data gets transferred along the direction of the arrow. And the way we've constructed it, it's acyclic, and in fact we always construct acyclic graphs in Dryad. We only support acyclic graphs. But as I said, this is a logical plan, and now we have some physical cluster that we actually want to execute it on. What we're going to do is talk to some scheduler and say, I have these 5 processes that I'd like to execute. Here are the inputs that they're going to read from. Pick sensible machines for them to run on. But this is all virtualized, so in fact the way Dryad's going to do this, at least today with Dryad Link, is it's going to do everything as push, and each of these arrows is going to be written to a file in its entirety before this guy starts to run. This guy won't start to run until all of its inputs have been completely committed to the file system by the guys upstream. So you can't. Dryad actually supports connecting these things with network pipes, but for simplicity of scheduling, particularly on large clusters where you really want to virtualize everything, we take the conservative route of writing everything to the file system, and then just pipelining as much as you can into one of these to avoid excessive I/O.
And also the fact that you're kind of really phasing the kind of execution, right? You're first, you only start this kind of second phase when everything here has been terminated, or is it kind of when all the inputs for this particular node? So could it be that like this one is already kind of getting the data while this one is still waiting for?
Right. So this particular plan, as it turns out, chances are that these are all going to finish. So this guy can't start until all of its inputs are ready. Yep. And chances are that these files will be written at roughly the same speed, assuming the distribution isn't too skewed, and it's a hash partition, so it shouldn't be. So chances are that these are all going to... So no, these won't start to run until all of these have completed, because they need to wait for all of their inputs to finish writing. However, if you had a more complex program, you might easily find that the plan looked something more like this, where you get common sub-expressions that get computed in parallel and then combined. And there, these will all start running in parallel, because this graph is just expressing the dependencies. So even though in this simple plan it actually executes pretty much in lockstep, stage by stage, in general we have lots of programs where that doesn't happen.
Yeah, but I'm just curious, kind of why, if you read kind of the MapReduce paper, right, there it also says kind of the next phase kind of only starts when all of these have finished. And so there also it has to do with kind of error conditions when when something goes wrong, that it's kind of easier to redo the work. Is that a concern as well, or?
So as I said, we actually support in Dryad connecting these with network channels, and in that case, these will all get scheduled at the same time, and then all run at the same time, and they'll just, this will block if this doesn't consume it fast enough, and this will block if this doesn't produce it fast enough. And so you can have them executing simultaneously that way. If you do that, then virtualizing the resources gets a lot more complicated, because you have to wait until there are 9 machines free before you can start these up. And there's an obvious fallback position that you could take, which is just to do cut-through. So you get these guys to write to disk, but you can optimistically start reading it before they've finished. And then, of course, you could run into issues. If these produce much more slowly than these consume, then you would essentially be wasting a computer, because this would just be squatting on it doing nothing. So, you know, you can shoot yourself in the foot that way. That is something that we're not actually supporting today, but it's sort of on the short list of things to do fairly soon, so we can experiment with it and see if we can tune it right so that we don't waste too many resources that way. But certainly if there are idle machines on the cluster, you'd think you might as well just start something up and use it. You can always kill it. So yeah, I mean, now that we get more into how the execution actually works, I mean, you brought up the fault tolerance in MapReduce. So, I mean, one thing that you should take away from the fact that I've just sort of drawn empty circles from all of these, even though they're actually running quite different code inside them. As far as Dryad's concerned, they're just some black box execution. It does something. So Dryad knows what its inputs are, knows the size of the inputs and the location of the inputs, but it doesn't know what processing is actually going to be executed. And there's a completely uniform state machine and fault tolerance model. It's not that macros behave one way and reducers behave a different way. So because we have this directed acyclic graph, there is some topological sort order. So even if you only had one computer in the cluster, you could execute this whole plan, because you know, if you just execute them in sorted order. So all the state machine does is it looks at each of the vertices and finds out which ones are ready to run. A vertex is ready to run when all of its inputs have been produced. It gives the scheduler a list of the things that are ready to run and the locations of their data. The scheduler looks at those and also the lists that have been given to it by all of the other jobs in the cluster. It uses some notion of fairness, so that each job gets some determined share of the cluster. It looks at the locality as well, and it tries to decide what is the most efficient thing to schedule next of all the things that are available. So then, you know, it chooses to schedule this guy, say, because this machine is free where its input data are. So then Dryad will run that to completion. That will write these outputs out to its local disk, and then that gets marked by the state machine as being ready. You know, once all of these 5 have completed, these guys all get marked as ready, sent to the scheduler. Then when they get scheduled, now, you know, ideally, as often as possible, something will be scheduled on the same machine as its input. So, for example, this guy should almost always be scheduled on the same machine that this guy was, so you aren't doing any network transfer. Something like this, of course, you're going to transfer almost all of the data across the network all the time, because that's how repartitioning works. So these will be scheduled more or less anywhere. And at that point, it pulls the data from wherever it lives. Now, if there's ever so if this process crashes, or if the machine reboots or something, then all that happens in the state machine is it gets marked as not as you know, to be executed again. It just gets re-executed. However, if it fails cleanly, then it will fail cleanly with an error code, and one of the error codes that it might give you is that it was unable to read one of these input files. And so you may find that, you know, the computer where this one wrote to has died, and so you actually have to backtrack and regenerate those inputs again. And so because you have this whole directed acyclic graph in the Dryad state machine, you can then just backtrack as far as you want, and it will re-execute everything it needs to in order to.
Okay, and so your scheduler will take care of that. That it kind of, you know, reproduces the necessary inputs.
Exactly.
And so
the assumption is that these things are deterministic, at least if they're not, you're going to get what you expect. I mean,
Yeah. Yeah.
So if you rerun it, you'll still get a legitimate result even if you rerun something.
Yeah. So that was kind of, you know, my next question is like, you know, you said like these nodes kind of, you know, there's like a state machine. So I would be quite interested to kind of know kind of, is there a particular interface or something, you know, that these nodes implement, or and does it have like, you know, do you have special like queues or something for it to kind of, you know, read stuff from the inputs and write it to the outputs?
Yes. So so one of these vertices, you implement the vertex. So this layer is all done in C++, and then
Good. So that was, you see,
Yes.
native code.
Well, I don't think Roger understood the question.
Yes. Yeah.
But that's fair enough. But only because perhaps we didn't ask it right. But continue.
Right. Yeah.
So the Dryad layer is all native code C++. Unmanaged C++. So in order to write one of the, you can just take the Dryad APIs and write yourself a raw vertex, as it were.
Okay.
And the way that you do that is you just override the main method of the Dryad vertex class, and then when that comes to be run, it's called with some structured block of data as input, which is sort of a generalization of a command line, and the list of a channel reference for each of the inputs and a channel reference for each of the outputs. And so all of the I/O is done using these Dryad channel classes, which are an abstraction for the actual data. And so that way you can slot in different implementations of these channels without having to touch the actual implementation of the vertex. So the things that are actually read down the channels are structured items. So if you don't want to deal with that, you can just so we have a standard item which is a buffer, which is just a bag of bits, and so you can just send buffers around if you want to. If you actually want to deal with data items at the C++ level, then the channel machinery all covers that. So the way Dryad Link uses this is it has a standard C++ vertex that implements this class, starts up a CLR instance, and passes handles to all those channels up to the Dryad Link layer. And the Dryad Link layer actually just uses the buffers in the native world and does all of the serialization in managed code, because it has all the type information that it needs to do that. But you know, you can certainly write things directly at the C++ layer, and we have for various reasons. So there's a particular idiom where you've got something that you want to broadcast to a lot of computers, and it builds a tree, and each of these is basically just a copy node.
Okay.
And that copy node just works at the native code level. It doesn't bother to come up to C# because it's not going to parse the data anyway.
Yeah. And so can you mentioned that you have a couple of different kinds of channels, right? So can you kind of, you know, tell a little bit more about that? So do you have like, you know, like for example, when you said, you know, if this guy writes something to kind of, you know, a local file, does it really write to a file, or is there kind of a special channel that's kind of persistent, or so is a file a kind of a channel, or?
So the implementations that we use in the external release are writing to a file, writing down a TCP pipe, and writing down an in-memory FIFO so that you can put two of these guys in the same process.
Okay.
Then if you have a distributed file system, as we have internally several distributed file systems, that has its own API for doing I/O, then the channel just writes to that abstraction instead. But certainly one of the prime channel writers is just, you know, doing write file.
Okay, so when you said, you know, this one writes to a file, does it write to a file in this distributed file system such that, you know, this guy can kind of read it from
So when you're doing the intermediate data, it depends on which cluster you're running.
Okay.
So in the HPC clusters, it's just writing to the local working directory of the vertex. And so we typically just do a RAID 0 stripe file system across all of the disks so that you can write at high speed just to local storage, and we try and we try and be smart about it. So the channel implementation looks at how many inputs and outputs it has and picks buffer sizes so that if you only have a small number, it won't do any writes less than about 2 meg. But if you have 1,000 outputs, it can scale down the buffer sizes. So
Okay.
And when you want this stuff to work right on the distributed system, you have to pay a little bit of attention to things like this. So if you're running a stage like this where each of these is reading from 5 inputs, basically as we discussed earlier, all of these are going to start at the same time.
Yeah.
And they're all going to read
exactly,
one input from here, one input from here, one input from here. So one natural way to implement whatever is going on in here, a natural way to implement it would be something that read the first file, then the second file, then the third file. And if you did that, then this machine would melt down.
Yep.
So
yes, because there's in this case 4 kind of machines.
Right, and so imagine there were 1,000 of them.
Yes,
this would not be so good. Mm-hmm. So wherever possible, like if your application logic doesn't actually depend on the order of these, then we randomize the order of opening them. And so we do a non-deterministic merge, basically, as the first thing in here, just so that, basic things like that you discover immediately if you go and implement one of these things, that you have to pay a little bit of attention to things like that.
Yeah. And so one of the things that you kind of mentioned that we would come back to, and in some sense here you do it kind of explicit, right? Here you have this kind of node that helps you to determine how to do the distribution here. But of course this kind of similar problem exists here, right? Where how do we know, like here, how many partitions we need here? So how does that work? So
this was so we talked a little bit about the API at the vertex.
Yes.
So there's also the API, so there's a process called the job manager, which is in charge of coordinating this whole job, which is the thing that holds the state machine in memory and manages this, deciding what to send to the scheduler when. And that also has an API which talks to a Dryad link piece, or in general whatever higher level language that you have, and so that API allows the Dryad link to build this graph, but it also it makes a callback to the Dryad link layer every time one of these vertices starts running or completes, and when it completes it says which computer it completed on and also the sizes of its outputs and inputs. And so at that point the Dryad link layer has enough information that it can rewrite the plan dynamically. So in this case, so Dryad link actually knows from looking at this that the total size of the data set being written out here is the same as the total size of the input data set.
Yes, yep.
So it can inspect these partitions, discover how large this output's going to be, and pick the partition number as a result of that. And in general, you can usually tell before you start executing something, what size its output's going to be, and if you can't, then you can write it to an intermediate. So something like this, before you start running this, you need to know how many partitions you're going to do.
Yeah. But that was kind of let me give you my kind of here my little puzzle.
Yep.
Because imagine that the lengths kind of vary kind of widely, right? Yes. So now I don't know, so maybe there's like, each of these is really huge, right? Because there's many different lengths. Mm-hmm. So now we've picked 4, but it turns out that really I want to have like 8. So
so the number of partitions here that you want has to do with the total size of the data, not the number of.
Yeah, but the size. But the size of the data now here is kind of, or what I want to say is each of these things is really big. So I want to kind of
Right, but you knew that when you started. How? Because the input data is the same as the output data.
Yes, but suppose that I would do a transformation here where I couldn't.
Yeah. So suppose you put in a select before this.
Before that, yes.
That did some unknown transformation.
Yes, or maybe just like a 2 upper or something where or something there. Yes.
So then, Really, that's up to Dryad Link to decide what to do. So it has two choices. One is it can make an estimate about what the size is going to be that it might get wrong, and the other is that it can actually insert an extra set of vertices that just, instead of pipelining the select with the group by, it could separate them out into two, and then it will know how large that was.
Yeah.
So, you know, but that's not really Dryad's job. It's up to the Dryad Link optimizer to make a sensible choice about what to do.
Yeah.
And you know, the more static analysis you can do on the code, the more likely you are to be able to make a good estimate.
Yeah. And so
and there's a lot of work that goes on actually using all of the reflection and things to do a good job there.
Yeah. So actually I'm more kind of interested in the kind of, you know, dynamic capabilities, right? Yes, because, you know, you can kind of statically analyze this, but, you know, how kind of dynamic is this? Can you kind of change the graph kind of, you know, on the fly and
so as far as Dryad's concerned today, any vertex that has not yet executed is completely fair game, and you can delete it, you can change its outputs, you can do anything you want.
And so who would do that?
So there are these callbacks going to the higher level. So Dryad Link would be so every time one of these things completes, the next layer up is given this callback, and it's given the entire graph, and it can do an arbitrary rewrite of that graph.
Okay, so let's kind of, you know, draw the picture here. So there's some other thing here that whenever, say, this thing terminates, it gets called back, and now this guy can say, I see here, and then I'm just kind of, you know, completely rewrite the graph.
Absolutely. So in practice, what I
and so how do you then know that how do you now know that kind of, you know, do you also kind of then backtrack across the kind of modifications of the graph?
So at the moment, you're not able to revoke vertices that have already run. There's no particularly good reason for that, and probably in a fairly soon revision coming up, we're going to make it possible to revoke it. So you can really backtrack right up to the beginning and change the plan completely.
Okay,
but at the moment, you can only go back to the frontier of things that have not yet executed.
Okay, and then, you know, so that makes it easy to kind of rerun all that was done before this rewrite.
So, in practice, actually, how a lot of these things get executed is.
It's an arrow here.
Yeah, I don't want to rub all of this out, but the plan, the graph that actually originally gets handed forward to Dryad, you know, usually looks something more like this very sort of abstract skeleton of the thing, and then the first thing that will happen is some dynamic grouping thing that will look at the sizes of all of these inputs and say, well, you know, if there's a bunch of 100 megabyte inputs on the same computer, we might as well just have a single, you know, so it will build, you know, maybe some dynamic tree there when it starts running. And so then the fact that this thing has now been rewritten and expanded to 2, that will propagate down, and that will expand this next thing into 2, and then, you know, they both go to the sampling thing, and then this thing gets blown up. And so often at the very beginning you just start off with this very simple skeleton, but as soon as you start running, it fills out with the.
So it kind of adapts to the kind of, you know, the actual.
Because here the number of vertices you choose at this stage is actually going to depend on the physical location of these things, and there are replicas, and the ones it actually chooses to use will affect the exact number of processing nodes that end up there.
Yeah. And so to go back to the kind of dealing with errors and so on, do you do something where you kind of, you know, you duplicate the computation, where you're kind of trying to run it on kind of multiple nodes to have like redundancy or something like that?
Right. So. And
is that something that you can influence as a user?
Yeah. So there's a default policy for stragglers. So as part of the API, all of these things would be explicitly grouped as being a stage, which is essentially a SIMD computation. They're all essentially supposed to be doing the same thing.
Okay.
And So there's a little plugin policy manager that attaches to this stage that gets these callbacks when things happen, and it has a default policy for using simple statistics to try and guess whether some of these things are running a lot more slowly than they should be, and firing off duplicates if they are. And so, because all of these things are supposedly deterministic and can be rerun anytime you want, you can just run duplicates and then take the output of whoever finishes first, and that works fine. So this policy can be swapped in if you have more information about it, but typically Dryad Link just uses the standard policy there.
And so is that based on callbacks, or is this guy kind of actively? So how does
it gets
flow go?
callbacks, and it also has a little timer in it.
Okay.
So it gets a regular call, and it can and you do all the obvious stuff. You throttle the number of duplicates that get generated in case the statistics are broken.
Interesting. I see some correlation between observable.
Exactly. So that's why I was kept asking whether it was
Sure.
like pull and push. Of course.
So within the the actual channel API, it has a synchronous API, but the preferred way to use it is with an asynchronous API. And so then if you attach several of these together within the same process, then it has kind of like an iterator model where all these asynchronous calls work as it's basically pull based. So the guys that are reading out of the file read spontaneously and then buffer up, and they block if it hasn't been consumed, and then it's pull based from the end of the tree all the way down to. So within the channel implementation, depending on the channel, you have that kind of iterator-based pull as well.
And so that's kind of interesting here, right? Because so in some sense you can make that kind of same choice here too, right? It's like if I have to read from 4, or what is it? Well, this guy has to read from this. 5. So at some point it has to kind of merge the inputs from those guys. So if it's a push model, that merge is kind of much easier than if it's a pull model. So is it pulling from these things? Because now but how do you know now when I'm pulling from this guy?
Mm-hmm.
This might take a long time, where maybe there's something already here. So you see what I mean? If I have to pull from 5 sources, I cannot block on one. But if 5 sources push, then I can easily merge the results.
Well, so let's assume you're doing a non-deterministic merge.
Yes. Exactly. It's like a non-deterministic merge is easier with a push model, right?
Is it? Okay. So the way we do it is
okay, good.
So we just have the asynchronous interface.
Yeah.
So you would send say 2 read requests down each of these things, and then every time a read completes, you send the next request.
Yeah.
And then now it just works, right?
Okay, so it's kind of
no.
So what you're doing is kind of a half push, half pull, right? Because you're making asynchronous call, and then you said you make 2, and then when they come back, you do the next one. Right. So it's kind of it's kind of half, right? So you're pushing or you're pulling asynchronously.
Yes, you're pulling asynchronously.
Yes,
that's exactly
exactly.
Yes.
Cool. Yeah. So that's you see, that's like these things are kind of subtle, right? It's like how do you kind of mix the various models?
Mm-hmm. Absolutely.
And the other thing is like we talked now like what are these things in the interface? So and that we can rewrite. So is there kind of what is the interface for kind of constructing these graphs?
So
how do you wire these kind of things up?
Right. So there's a C++ interface for building these graphs where you new up a vertex, and then you can replicate it, and then you have a handle to that set of things, and you can connect sets together. So you would make yourself this object that corresponded to these 4, and this object, and this object, and then you would say connect this to this, pointwise, connect this to this pointwise, you know, connect this to this with a cross product, and it just wires in all the edges. Now, if you want to, you can go in and manually put in any kind of asymmetric edge construction you want. You can wire them up by hand, but we have these convenience methods to do the standard.
Okay, yeah, so because that's kind of...
We do also have some graphs that are quite irregular.
Yeah, but even, you know, I think this is a very, very nice point, because if you're building these things, it would be really kind of, you know, nasty if you would have to kind of, you know, build all these and kind of wire them all kind of individually. So you have kind of high-level combinators to build, kind of, you know...
So I can tell you the first time we did it, it was a failure, and the second time has worked a lot better. But what we don't have a good interface for at the moment is rewrites. Rewrites are still ugly, and we need a higher level way of doing that. We need to go back and look at that.
Yeah, because, you know, it's like it's very hard to have a nice kind of library for building kind of graphs in general, and this is not even just general graphs, right? And then graph rewriting or kind of, you know, DAG rewriting is not easy to kind of, you know, to specify.
You know, in full disclosure, in the history of the project, when we built Dryad, we thought that developers were going to use these Dryad interfaces, they were going to build graphs, they were going to write vertices, and, you know, we waited and they didn't come. And then Yuan Yu realized that Link was a very good match and built Dryad Link, and then, you know, people actually wanted to use that. But, you know, so now we think of Dryad more as a intermediate execution layer, but we didn't know that when we started. We thought we were building something to program against, and it turns out that nobody wanted to program at that level of abstraction. Okay. And if we had better interfaces for doing these things, I mean, I think, you know, Link is a great way of building graphs like this. Which was the thing that Yuan sort of saw, was that...
Yes. No, I 100% agree with it, but it's like it's a way to build specific graphs,
that's right?
So, and in sometimes...
But what we found is that there's not a lot of takers for building the other...
But for example, like if you look at things like Windows workflow or something, in some sense that's kind of, you know, similar, right? Where you build some kind of, you know, control flow graph, or, you know, or some data flow graph. And
so there's what is it? SDSS, SQL Data Services.
Yeah.
So another group within Microsoft actually built a connector for that to Dryad, and that does build quite irregular graphs just by looking at those workflows. So that, you know, there is one customer who's done that, but in terms of people just working out when they have a specific application in mind and writing down the graph, it doesn't really happen.
Okay, so in some sense it doesn't really matter how hard it is to build the graphs, because there's another abstraction on top that kind of generates...
But
and it has to do with the kind of programs that people are writing, which is... you know, it turned out that there were lots of people that wanted to write programs that you could write as Link programs and still distribute them on our clusters. And there's a much smaller number of people that want to write the fine-grained...
Yes.
So it worked out well as an abstraction layer for Dryad Link to talk to, but we haven't found that many users of the...
So from a high level, they had to use Link, right? Because that's the only way they could break the computation up into meaningful chunks and then execute them asynchronously and put them together.
It's the best way integrated with a language that we know about.
That's what I mean.
So in some sense, again, you know, we mentioned that yesterday, Link is kind of like a scripting language, right? It's just a way to script this computation, and then, you know, here, you know, you generate that computation, and then there's the scheduler that it kind of, you know, then actually execute the computation.
Absolutely.
So we think of it as a kind of hybrid between imperative and declarative, that as far as the programmer is concerned, you're writing this imperative sequential code, and then the lazy evaluation in Link hands over this big chunk of stuff the programmer thought was imperative, but all it was doing imperatively was building up this AST, and then you get the declarative optimizer gets to come in and do its work.
Beautiful.
Yeah. And so, like another, when you talk about Link, and we keep talking about that, you know, for some reason it's like, you know, F sharp, right? F sharp.
What do you mean for some reason?
For some reason, well, because it's a fundamental thing too, right?
Yeah.
So with F sharp, with its kind of workflows, have you worked with them to kind of, you know, map them to Dryad as well? Because that seems to me like also kind of a very natural match, right? Where you can write your workflows even more imperatively with the kind of async workflows, and then just map them onto this.
People have written F# programs that have been executed on Dryad. I am actually not fully up to speed with all the things that people have done. I think the main way that people have done that is to write link in F# and then use Dryad link under that. I don't know if anybody's tried to go directly from F# to Dryad. It's an interesting question. We've talked with Simon Peyton-Jones about Haskell as well.
Yeah, yep. Well, but that's the beauty of kind of using kind of native code here, right? That you're kind of fully kind of generic. It's like it doesn't really matter, and I think that's important, right?
Absolutely.
That the underlying computational framework is independent of whatever runtime you want to use.
Beautiful, and it should be, because I mean, and this is the way that you guys are marketing Dryad now, and the way that you started marketing it yesterday. I mean, at the end of the day, the developers, the vast majority of them, way up in user mode world, right? The composers, they don't really want to explicitly think about this.
Absolutely not.
That's not their job, right?
Right, and also there's a big body of knowledge that you have to build up before you can write the right plan down.
Precisely.
And that's
like
what the optimizer's supposed to do.
Yeah.
So to prevent you having to learn that.
Yeah. So let's talk a little bit about the engine more, right?
Yep.
So you get this graph that you understand, and then something happens, which we've talked about. I mean, there's an execution engine.
Yeah, so you said, you take the topological sort of this thing. Is that the level of detail you want to go in?
I thought it would be kind of
great.
cool.
I drew kind of a picture of the cluster, which
that would be great.
From a high level to figure out what's actually going on.
Because I'm lost in vertice world now. I want to step back into reality for a little while.
So you've got some cluster with a bunch of computers on it, and you have a scheduler, which is a shared service in the cluster, and this is behind some firewall, and you have a client machine over here. And so the client is, just writing some link program, and then when they hit run, every time Dryad link passes over one of these little declarative blocks to the Dryad link provider, it goes away and it generates an execution plan using its optimizer, and it compiles a bunch of DLLs for the code that's actually going to be running in these guys. Okay. So it works out what should be pipelined together, actually invokes the compiler and generates those DLLs. And then it ships all of that. It ships the plan and the code through the firewall to this scheduler and puts it in a queue. So the scheduler is doing some kind of admission control. So typically we have some maximum number of jobs that are running on the cluster at any given time. So once it becomes one of the 10 most recent jobs or whatever, then this thing picks a computer on the cluster and it fires up the job manager. And the job manager is this process we talked about that actually contains all of this state machine. So then the job manager starts running, it consumes the plan from here, it starts doing all of these callbacks to find the number of vertices it needs and stuff. And then every time these vertices are ready, it writes back to the scheduler and says, here's a list of the vertices that I would like to run, here's their inputs and the data sizes. The scheduler has requests like this from a whole bunch of job managers from the other 9 jobs that are also running on the cluster, and it tries to do some kind of global optimization to work out where good places to run these things are, and then it writes back to the job manager and says, okay, you're allowed to run vertex number 2 on computer C here. So at that point the job manager talks to a little daemon on this and says, please start up this, and it tells it the resources that it has to fetch, either from a distributed file system or it just copies them across. So then this thing starts running, and then the state machine's just sitting there waiting for something to happen. So it sends little heartbeat messages back and forth to leases to make sure this thing hasn't crashed. When it completes successfully, then it moves on to the next thing in the state machine within here, and it'll send a message to the scheduler saying, this guy's finished, but here's some more guys I want to run. If it fails, then it does the backtracking as we've discussed. Again, asks for more. Now, suppose this thing started up, somebody gets into work early, and they're the only job running on the cluster, and they have all 300 computers for their job that it's actually doing useful work on. Then somebody else comes in and they send another job to the scheduler, then the way we have it configured today, the scheduler is actually going to say, all right, I'm sorry, you only get 150 machines each. So it's going to, based on the things that are currently running and the new requests, it will pick its best idea of the 150 to kill for this guy. It'll tell this guy, all right, sorry, you've lost these machines. It'll go off and kill all of those. Again, backtrack through the state machine so that it just has them as
okay, so from the perspective of this thing, it's just as if these machines suddenly failed.
Right.
Yeah.
So, I mean, it has their error code, so it won't... So, I mean, the other thing, of course, that it's doing is when there is a failure, it has to go tell somebody so that if a machine genuinely isn't working, you stop using it.
Yes, yeah.
And so, you need to keep track of whether it was a real failure or a planned kill. But yes,
So
in terms of what happens next, it's exactly the same.
I was just going to say, so do you know, like, up front how complex the computation is going to be? I mean, how
sometimes you do, sometimes you don't.
Okay, so you can dynamically allocate more distribution, is my question.
Yes, so typically the way... So when we're trying to share the cluster, suppose we're sharing a cluster of 300 computers between two jobs.
Okay.
What we typically do is, if both of them have requested 5,000 vertices, then they'll each get 150. Mm-hmm. But that's not an allocation of 150 specific computers. That's that at any given time, you'll have 150 on this guy and 150 on that guy, and the actual set of which computers are being used will vary depending on the data that they're trying to read.
Interesting.
And then, of course, if one of them gets near to the end or is in some phase in the middle where it hasn't got much running, then maybe it'll only have 10 and the other guy will get 290. I mean, these grow and shrink.
Of course.
Okay,
Awesome.
okay, because that is kind of, even if you look at this picture, right, it might need less or more depending on which phase it is.
And almost all jobs have that kind of pattern, and so you really want to keep the cluster loaded all the time. You can do a lot better than,
Yes. Yeah.
Most jobs do not occupy the whole cluster.
And so one thing you mentioned here is that the state machine that this thing keeps, right, is based on some kind of topological sort of this graph. But since this thing can be dynamic, right, it
doesn't
really
keep resorting it. I mean, you just keep the little count of the number of inputs that are ready.
Oh, okay, yeah. So that was
yes,
and then so you can just have a dynamic queue of things that are ready.
Exactly.
Yeah.
So when something finishes, it just looks down all of its outgoing edges and increments the ready count, and then if it's goes into the queue if it's ready.
Okay, yeah. So that's that sounds kind of like once you kind of make this thing dynamic, then kind of trying to figure things out like early seems to be like okay,
right. So
your assumptions are kind of immediately negated the next time there's a change.
Yeah, we do a sort at the beginning just to find out whether or not it was acyclic, and also as an easy way of finding the guys that are ready at the beginning.
Yes.
Because you have to do it somehow.
Yeah. So in terms of your topological vertice map, how much can you guys scale today? The thing you released yesterday, like give me some numbers.
We.
If that's the question even makes sense.
Yeah. But, so I mean, millions of vertices in a job from end to end, and thousands concurrently executing.
Thousands.
Yeah.
And so
that's how far we have scaled. I don't know when it would fall over. So in my experience, each time that we increased the cluster size by an order of magnitude, we found opportunities for lazy optimization. But each factor of 10, there is something that we actually had to go and tweak, some data structure that fell over and we replaced it.
Amazing, really.
Yeah. So and like, what is the kind of biggest graph that you kind of have ever run? Like how many? I mean, I assume that you have like you write tests that just kind of generate some kind of
Sure.
Yeah.
giant thing.
I can't actually tell you that. The reason is that we're not the ones that do that. What happens is some user comes along and writes some program that they didn't realize what was going to happen, and that will generate an enormous graph. And if it completes, they're not going to tell us.
Yes. But if it fails, but it doesn't, it can fail if you're
I don't really have a good answer for that. What we should have is a log of every job that's ever been run, so I can answer questions like that. But unfortunately, we haven't got quite that.
And so talking about like as the kind of topological sort, but if you're not doing this, if you're doing this using a dynamic scheduler, why do you restrict this thing to be acyclic? Because in some sense, it should be okay to have a cycle in here.
Well, so the way I described it, if you had cycles, this will never run because this can only run when its inputs are ready, and this can never be ready because this hasn't run. So, but if you have them connected with network pipes, then there's no reason not to have cycles.
Yeah, or usually when you have a thing like that, there's some kind of delay or some initial value in there to just get the cycle going.
So we could certainly put that in. It makes the fault tolerance more complicated because then, suppose you have this cycle like this, and this guy fails.
Yep.
Then you really have to go and find the whole component with the cycle in, and discard all of it and start again because you don't know how many times it had gone round. And so there's no reason we couldn't do that, but it just adds a little bit of complexity.
Yeah, you have to find the kind of strongly connected components in here, and those kind of all
you have to fail them as
yes.
And you can actually, you can maybe do a little bit better. I mean, one of the initial motivations for having the channels send strongly typed items instead of just bags of bits is so that you can maybe recover from some of that by just, if you have some buffering and you could ask this guy to replay, then, if you knew that this failed after 100 items, you could say, can you just give me 100 items? And they don't have to be bit for bit the same if they've got timestamps in them or something, But we never actually used that. But that was an initial motivation. Yes. And essentially we haven't found we haven't really found people who are asking for it. But I think as we move more into more traditional HPC applications, so I've been trying to do some training of large distributed neural networks, and you have a fairly tight loop of communication because you're doing updates that depend on each other of large sparse matrices, the kind of thing that you would traditionally maybe use MPI for. And when we have a loop in Dryad Link, what happens is you unroll it statically.
Yes. Yeah.
And as you start to want to have termination conditions and more sophisticated things, cycles start to be more appealing, and we're probably going to try.
Because in some sense, at the moment you said you can dynamically kind of update the graph. Now you can simulate cycles, right? By every time you just kind of unroll kind of one thing, such that kind of funny,
so you can do that with the current API, but it's maybe not the best way to do it.
Yeah. I mean, it's a cycle more than kind of an infinite kind of unfolding
you don't necessarily want to actually materialize.
Yes, exactly. So that's very interesting. And another thing when we talked about the backtracking of failure, so how? I mean, maybe you also again you don't know the answer to that, but I'm curious, kind of how kind of deep is usually the kind of backtracking. Is that
not very?
Yeah, that's kind of what I would expect.
But I don't have good statistics on like the worst case, but not very deep.
Yeah.
I mean, really, I think the reason for that is that that with modern server computers, failures are rare, and I mean real failures are rare, and transient failures are common. So most of the reason that you're backtracking is because something has failed for 5 seconds, 5 minutes, whatever. But it's not that you've actually lost a whole pile of data.
Yeah.
So you need to be able to tolerate. You need to be able to continue even when you lost your network connection. But
yeah. Because if the kind of this backtracking would be really deep right now, this thing would kind of never terminate, right? It could kind
in principle, yeah.
Yes, and so. But yeah, that's would be my intuition too. I don't know why.
But no, I think if it were very deep, we would have noticed and we would have had to do something else.
Yeah, and then probably you want to kind of explicitly kind of partition your computation into kind of parts, right? That kind of
right. So of course you can materialize to the file system halfway through if you want to.
Yeah, and then you can mitigate against that. Cool. And so, like, you know, talking about like lines of code, right? You know, how like the whole kind of Dryad, you know, is that like, you know, millions of lines or you know?
No, but so I think all of the C++ with all of the test code and a bunch of sort of helper classes is closer to 100,000 lines than I would like it to be. I think one of my jobs over the summer is to delete a lot of that.
Yeah, so that's kind of what I like my kind of developers, you know, negative productivity. I think that's the best thing, you know, the best people you can have, that kind of, you know, check in less code than, you know, or negative amount of code.
It's kind of loaded up, and some of that is for things that, you know, we implemented that turned out not to be that useful, and we just haven't deleted yet.
Yeah, and that's obvious. Like, you know, when you do a research project, right? Then you're kind of, you know, trying to get, you know, and as you said also in the beginning, you assumed that this would be the scenario. It turns out that people are using it for other things. So,
and things like, you know, I said we had these 2 graph builder APIs. Well, for legacy reasons, we actually left the old one in there, and you know, we've managed to get rid of everybody using it now, so it's time to delete it.
So in terms of language choices, right? So C++ wasn't the only language you could have implemented a system like this in, right? I could think some maybe even Erlang or some highly crazily concurrent language. Or so here, let me ask my simple question: why did you choose C++ to implement it? That's all. Not as saying why didn't you use C#. I mean, you wouldn't want to use C#. You wouldn't want the CLR or the footprint, but just curious. That's all I'm asking. Is a simple question. So,
I mean, the real reason is that I had just come off 18 months working closely with the search dev team, implementing a bunch of stuff in the search index serve pipeline, and was fully up to speed with C++ and writing this kind of code in C++, and it was the easiest thing for me to do, and also we wanted to integrate it with the search code base. Yeah.
And the funny thing, Charles, you know, when you're saying, you know, oh, maybe Erlang, but the thing is that, you know, I think the real question you ask is Erlang itself written in Erlang, because at the end you get something that's highly concurrent, but you know, the code here, all these things are not concurrent, right? Well, so it's it's like at a different level.
Fair enough.
This whole state machine, right? Single global lock, right? Because there's not a lot of concurrency in here. So there are multiple threads inside the job manager, but the purpose of the multiple threads is for doing communication. The actual logic is just a single lock, no messing around, none of this fine-grained locking, you know, trying to write bugs for yourself. It's perfectly fine, and until proven otherwise, I just started out with a serialized state machine update, because state machine updates are quick in general.
Yeah.
But the other part of the system, the actual execution of all of this, has to be concurrent.
Yeah, right, so the execution is concurrent,
right?
But so the controller, it's like, you know,
and so the execution at the low level is using all of this this asynchronous poll stuff, which is very easy to do in C++ with completion ports. You know, that just, it's sort of designed to work well with that model. At the higher level, the Dryad link code that's executing is using plink, so that we don't even explicitly see the concurrency at all. We let devdiv do that for us.
Nice, and they do.
And they do.
Yeah.
Joe Duffy.
So, exactly.
Yeah. So that's kind of, you know, another interesting thing that we kind of touched on kind of briefly yesterday, right? That there's kind of, you know, several kind of layers of abstraction and concurrency, kind of, you know, all kind of telescoping. You know, so you first take this link query. You build this kind of, you know, this graph, but then each node itself can be, you know, recursively as a fractal kind of, you know, have plink, which again itself builds a plan and runs it on the multiple cores, and then probably inside the kind of, you know,
in the cores
there's something going on. It's like
totally. So fractals, yes. So you guys employ fractal mathematics,
absolutely,
obviously.
of course.
Cool. So we're running a little bit low on time. I know you have a bunch of meetings. Yeah. So do we have time for one more question, or?
Yeah, so kind of, you know, and I don't know if you can talk about this, but you know, you ship this now to external people, researchers, and are there any kind of, you know, uses within Microsoft and that use?
So Dryad is being heavily used in the search backend to do a lot of their batch computation on the very large amounts of log data they have, and all of the largest clusters are are in the search production environment running Dryad.
Okay, so when we were talking to Harry
Yeah,
about
who's in
that, so
this building.
there
Yeah.
was like
Right, so they actually they have their own language called Scope, which
Yes.
runs on top of Dryad in their environment. They aren't using Dryad Link at this point, but it's all running using the same execution engine.
Okay, and Scope,
Yeah,
you can find that paper on the web. It was published at VLDB. It's a kind of a more SQL-ish language.
But at the end of the day, all a language has to do is be able to output that kind
Exactly.
of AST.
That's right.
That you can then build this sort of comprehension
Right.
of vertices.
Yep.
Very heavy. Now, I do think I understand what Dryad means. These things
Yes.
go deep, man.
Yes, yeah, of
I
course.
love these.
Yeah.
But I think the people in the audience they understand what Dryad is now. I
Yep.
hope.
Right.
I mean, we kind of started off pretty deep, but it was great to put a face behind some of the science here. So
Yep.
really good job, man.
Thanks a lot.
Thank
Yeah,
you.
great. And again, right, this is all available for people to play with.
So play with it.
Yep.
But let
great.
me ask one question though,
Yep.
real quick, when we say that. So if I'm a dev, and a lot of Niners are, they're pro devs, but they work maybe in small shops, got an extra dev machine in their garage or two. How would they be able to build a little Dryad system to play around? So in other words, they can't just go to Azure, because Azure doesn't implement this yet, right?
Right. So the thing that we've released is really the Dryad Link programming layer. You can't directly program Dryad. We haven't released the Dryad APIs yet. That hopefully is coming soon. So it runs on top of the HPC cluster. So if you get yourself, a 2-machine HPC cluster, you can run yourself a 2-machine Dryad Link cluster.
Cool. Excellent.
All right.
Thank you, man.
Well,
great to see you, dude.
Yeah, this was nice.
Yeah.
And so then next time we should then talk about Dryad Link.
Yes.
Right. So then we kind of we went
We got the Dryad part. Now we can break
Yes.
apart the Link part.
Exactly. Perfect.
Excellent.
All right.
See you next time,
guys.